In Rome, a building called the Pantheon has been standing in continuous use since the year 126. The dome above it is unreinforced concrete. No rebar, no steel skeleton, just a single continuous shell of poured rock that has carried its own weight for 1900 years. Off the coast of Israel, there is a Roman harbor at Caesarea Maritima. Its piers were poured directly into the open Mediterranean 2,000 years ago, and they are still down there. Salt water is the single most destructive environment we know of for concrete. It chews through modern marine structures in 50 years or less. And yet here is a harbor that was poured before Christ was born, and the rock has grown stronger over time, not weaker. The thesis of this video is simple. The Romans were doing something we are still not doing, and the gap between us and them is wider than it has any right to be. Chapter 1. The Buildings That Should Have Fallen. The Pantheon's dome is the largest unreinforced concrete dome ever built, by anyone, anywhere, including us, today, with everything we know. 43 meters across, with no internal supports. The Romans poured it, struck the wooden framing, and walked away. It has needed no structural intervention since. It is not a lucky survivor. Across Rome, the same material did the same thing again and again. The baths of Caracalla covered an area the size of a small town, roofed by concrete vaults 30 meters in the air. Large sections are still standing. The Basilica of Maxentius held up coffered concrete ceilings so vast that Renaissance architects came to measure them, trying to work out how it had been done. Aqueducts, bathhouses, breakwaters, harbor walls, sewer systems, across an empire spanning 3 continents, all poured from the same family of recipes. Most of those structures are still measurably intact. Some of them are still in everyday use. Now hold that against the concrete of our own century. Most 20th century concrete construction was designed with a service life of 50 to 100 years. Not as a worst case, as the plan. Bridges built in the 1960s are already being demolished. Apartment blocks from the 70s are losing structural integrity. Overpasses are inspected and replaced on a rolling schedule because the concrete is simply wearing out. We are not, as a rule, building things that will outlast us. The Romans did it casually, for 4 centuries straight. And the strangest part is that the recipe was never lost. A Roman architect named Vitruvius wrote it down in detail in the 1st century BCE. The ingredients, the proportions, the regions to source the materials from. And yet for the next 2,000 years, every careful attempt to follow that recipe produced concrete that did not behave the way the Romans did. Something else was going on inside those pores, and for 20 centuries, nobody could work out what. To see why it stayed a mystery for so long, you have to understand what we replaced it with. Chapter 2. What we build with now. Almost everything built today uses one chemical system. Portland cement mixed with sand, gravel, and water. It was patented in 1824 by an English bricklayer named Joseph Aspdin. The name came from the color. He thought the cured stone resembled the pale limestone quarried on the Isle of Portland. Portland cement is fast. It cures hard within days. It is consistent, predictable, and cheap to manufacture at enormous scale. And that is exactly why every building you have ever stood in is mostly made of it. But that scale comes at a cost most people never see. Making cement means firing limestone in a kiln at around 1450 degrees. That releases carbon dioxide twice over, once from the fuel burn to reach that heat, and once from the limestone itself, which gives off carbon as it breaks down. Taken together, cement production accounts for roughly 8% of global carbon emissions, so it is carbon expensive to make. And it has a second problem. When it cracks, and it always cracks, the cracks just keep growing. Water works into the crack. If there is steel rebar inside the concrete, the water rusts it, and rust takes up more space than steel, so it forces the surrounding stone apart. If there is no rebar, the water freezes, expands, and widens the crack on its own, winter after winter, until the structure can no longer hold itself up. Either way, the building dies, and the entire infrastructure of the modern world, every bridge, every dam, every parking garage, every foundation, is built from a material that, structurally, has the lifespan of a single long human life. The Romans, by contrast, were pouring a material whose cracks, on contact with water, did the opposite. They closed. Nobody could explain how until 2023, and the answer turned out to be stranger than the engineers had been guessing for 200 years. It had been hiding in plain sight. in samples researchers had held in their own hands for decades. Chapter 3. The Reservoir Inside the Stone. In 2023, a team at MIT, led by a materials scientist named Admir Masic, took thin sections of 2,000-year-old Roman concrete and studied them at the scale of individual grains. They used high-resolution imaging and chemical mapping to see exactly which elements sat where, down to the scale of millionths of a meter. What they found confirmed something every Roman concrete researcher had seen and ignored. Tiny white chunks of lime, a millimeter or two across, scattered through the matrix like flecks of sugar in dough. For 200 years, those white chunks had been treated as proof of sloppy work, evidence the Romans had simply mixed their lime badly. Masic's group turned that assumption over. What if the lime chunks were not a defect at all? What if they were the entire point? Their conclusion was that the Romans mixed their concrete with quicklime, raw, unslaked lime, and did it hot. The technique is now called hot mixing. Hot mixing leaves behind lime chunks that are still chemically reactive. They are, in effect, tiny dormant reservoirs of unspent lime, sealed inside the stone and waiting. When a crack forms and water seeps in, the water reaches one of these reservoirs. The lime dissolves, flows into the crack, and recrystallizes as hard calcium carbonate. The crack seals itself, not as a figure of speech, chemically, with the very same material the building is already made of. The team tested the idea directly. They poured Roman-style concrete in the lab, deliberately cracked it down the middle, and ran water through the gap. Within 2 weeks, the crack had healed shut, and water no longer passed through it. A control sample of modern Portland concrete, cracked and watered exactly the same way, never recovered. 2,000 years of mystery, settled by one careful experiment. It also explained the harbor. In seawater, the same reactions kept forming new, interlocking minerals, which is why the Caesarea piers grew stronger as the centuries passed. Which leaves one obvious question. If we now know how it works, why are we not building this way? The answer is not one thing. It is 4. Chapter 4. Why knowing is not enough. The first reason is that the Roman supply chain no longer exists. Roman concrete leaned on a particular volcanic ash from the Bay of Naples, called pozzolana. It reacts with lime to build the tough, durable mineral phases that hold the whole matrix together. There are other volcanic ashes around the world, but none is chemically identical to the Italian one. The hot mixing method matters more than the exact ash, but a faithful rebuild of the Roman supply chain would still mean quarrying at a scale nobody is set up for. The second reason is speed. Roman concrete takes weeks, sometimes months, to develop its full strength. Modern construction schedules expect a pour to be load-bearing within days. The third reason is regulation. The modern building industry runs on certified, standardized mixes. A new concrete recipe has to clear years of testing before an insurer will let you pour a foundation with it. And the fourth reason, the one that is hardest to say out loud, is that nobody is paying us to build things that last 2,000 years. Developers want a return on a 30-year horizon. Governments work in election cycles. The market does not reward durability that only pays off in the 23rd century, none of which means the work has stopped. The MIT team has since founded a company to bring hot-mixed, self-healing concrete into real construction. Other groups are chasing the same goal by different routes. And the carbon cost of ordinary cement gives that work something it did not have before. A powerful reason for the industry to actually change. A material that lasts longer is poured less often. A material that heals itself is repaired less often. Both of those mean less cement fired and less carbon released. So we know the chemistry. We have the recipe. We have the peer-reviewed paper. And for now, we are still mostly pouring Portland cement. Knowing how a thing is done, it turns out, is a much smaller part of doing it than we like to pretend. The Romans had something that no single formula can capture. It was a civilization that valued the result enough to organize itself, for centuries, around producing it. Their concrete was never just chemistry. It was a habit of mind, poured into a mold. And that habit of mind is the part we actually have to recover. Because the chemistry, on its own, was never the hard part. Chapter 5. What outlasts us? There is a reflex in modern engineering that goes, of course we are ahead of the Romans. Of course we know more. Look at our materials, our machines, our computers, and in almost every way, that is true. But there is one axis where it is not. The Romans built things they expected to outlive them. We, mostly, do not. Their concrete will still be standing in the year 4000. Most of ours will be rubble before this century is finished. That is not a chemistry problem. It is a long, slow, collective choice about what we believe we owe to people who have not been born yet. The Pantheon was poured by people who would never see it reach even 100 years old, let alone 2000. They built it that way regardless. Their buildings are still here. Their reasoning, we are still trying to recover, and the longer we wait to recover it, the more of our own century quietly turns into rubble we will have to clear, before we can pour anything built to last. If this was worth your time, the easiest way to see more of it is to subscribe. There are other stories like this